Great, so we're ready to go. So I'm going to talk about something very much materials related, so I hope I will be able to convey to you. I don't know how many of you are into materials and modeling of materials, so that's what I'm doing. This is work that has been carried out in Leoben. Here are my collaborators, and I want to emphasize Alexander Reichmann, who really is doing what is on the title, the implementation of a NOMAD oasis in our lab for sharing of grain boundary segregation data. So this is my outline. So I would like to first of all give you a little bit of an introduction on grain boundary segregation. This is the materials related aspect that I want to convey to you. Then I want to give you maybe the point which is most dear to us. We want to compare actually approaches which come from simulation, from density function theory, which will link then to segregation. I want to see how well does that work and how predictive are we in predicting materials properties. And then I will come to the implementation, as I said, and as a last point, Alex is going to demonstrate it. He's not here, he's joining us online. I hope that will work. Let's see, I'm excited. Okay, so why are we caring about grain boundary segregation? So here you see a microstructure of a material. This is molybdenum, but many materials look like that. Actually, there are grains inside, right? And what we really care about is knowing what goes on at the grain boundary in terms of the chemistry, because that can be completely different than the one in the bulk, right? So here is, I show a result from an atom probe tomography experiment. You see there's lots of boron and carbon here in this case on the grain boundary. And so the chemistry here is completely different. And actually many materials producers do not know what kind of chemistry they have on the grain boundary. It's difficult to measure and expensive to measure and can change also, because even very small amounts of some solute can actually enrich strongly. ppms of boron are enough to show up on the grain boundary, for example, right? And so we talk, or what we care is, of course, intergranular embrittlement phenomena. And since I'm from Leoben, I have to show some cracks, right? So here, this is my slide. So intergranular embrittlement happens when you have solutes at the grain boundaries which weaken the grain boundary, and then you have cracks which run along the grain boundaries, and that you don't want to have. And a lot of alloys have this problem. I just show a few here. Iron, this is tungsten, this is nickel. So you find this very frequently, and we want to be able to control this, right? So this is not the only point, but this was the main driver to understand segregation for us and for many other DFT-related activities. But I just mentioned here there are many other properties that one can also understand when knowing the grain boundary state. And what we do with DFT now is that we typically run calculation of grain boundaries. Here is a model of a grain boundary. And what we calculate is how a solute actually feeds the grain boundary in terms of energy. So you see here, for example, a rhenium atom in tungsten going through the grain boundary actually feeds attraction, which is here a complicated profile, right? So it's not just one number that we need the binding energy, but we need actually a lot of numbers and to understand the attraction of a solid into the grain boundary. Okay, so we are here. That's what we do with DFT. Then, if you want to compare to an experiment, what we need is then to couple other simulation methods to that, so that we can really do something with or compare to an experiment, actually, right? In an experiment, what people measure is, for example, when a sample fractures, right? When it's brittle, when it's ductile, at what temperature that transition happens. And for example, also, I will show examples on this later. Or an experiment can tell me how many atoms I have on the grain boundary, and other complicated phenomena. So this is where we can really compare with experiment. The segregation energy itself that we get from DFT, we cannot compare directly, right? And this is now all going to be related to showing you that in terms of, let me go back here, in terms of mechanical properties, I think we have a pretty good understanding which solids are good for grain boundaries and which ones are bad for grain boundaries, right? So I show here a result from DFT calculations. For this grain boundary, we see all green elements are good for the grain boundary here in iron, whereas all red are bad elements. They reduce the cohesion, and then we get this breaking at the grain boundaries. And this is an early work actually from '89, where they have already identified these solutes as bad cohesion weakening elements, and we see that we have a quite good correspondence, and we also get carbon here as a good element, as it was already identified previously. So here is another example for showing you that we can actually describe this cohesion effect quite well. This was a very interesting experiment which showed that the same basically alloy can change the fracture. Here we have an intergranular fracture where the crack ran along the grain boundaries. And here we have a different fracture mode where it did not run along the grain boundaries. So that's very interesting. We see the transition occurring basically by putting more hafnium into molybdenum, right? And then we got the change in fracture mode where you think, okay, hafnium is changing the grain boundary, right, somehow. And makes it strong because it doesn't break anymore at the grain boundary. And what APT experiments show that it's not due to hafnium, but it's rather due to other solutes which are there because we cannot control perfectly the chemistry, but by chance carbon and boron enriched very strongly at those high hafnium levels also, and oxygen was depleted from the grain boundary. And this is something which was really measured by a lot of grain boundaries here. And so one actually can understand why these grain boundaries are stronger, because they have a different chemistry, first of all, and we can predict that actually boron, carbon, from DFT now, these are DFT simulations, as we have seen before now from Molly, there are really good elements also here, and oxygen is a bad element, and we see that the chemistry here is just more favorable in terms of the cohesion, right? So cohesion, I think, is a topic which we can understand very well. What is much more difficult is actually to understand why we have a certain solute at the grain boundary. And that is something we are really working on now to get predictive also in that respect. So basically, we're talking about the grain boundary excess that we want to understand. Grain boundary excess means the enrichment of solids at the grain boundary, right? And here I show an early example that we have done for rhenium in tungsten, where we have basically now calculated a lot of segregation energies, which are shown here by colors. Dark is strong segregation, and white is 0. And we plug it into this equation here, which links, this is a thermodynamic model, which links our segregation energy to a concentration, which then gives us the excess, right? Which is calculated here. And the important thing is that we had some measurements in the literature here. This is atom probe field ion microscopy from '91, actually, very early and very nice work, which has shown here for grain boundaries, for example, when we have 25% rhenium inside, at the grain boundary we have almost 75% of rhenium, right? Much more. And a lot of grain boundaries were investigated. Here, every point is a different grain boundary. And we have done the calculations with the FD, and we see we get reasonable agreement, not perfect, but I think very good agreement. So also in terms of the excess, I think we can do quite well for this simple system. It's just a binary alloy, rhenium and tungsten, that's it. But if we go into a more complex system, the one that we have seen before, where we have many solids and we have also these ppms of some solid inside, like boron here is just present, like 5 ppm, 7 ppm are enough that you completely cover your grain boundary, or you significantly cover your grain boundary with boron, right? And that we see here, and to predict these enrichments is very difficult. So here I just show a result that we have obtained. So if you use the same framework, and you do not take into account, for example, precipitation, you would get completely rubbish in terms of the chemistry. We would expect oxygen everywhere, and so this is the APT result, which has a lot of carbon here and boron. If we just take the model that I've shown before, we will get a lot of oxygen, completely wrong. If we include precipitation, then we get reasonably close. So we see that actually carbon we can predict quite accurately here, but we do not match everywhere. And for example, hafnium depletion we do not see. So there are certain things which do not match so well. And for that reason, we need more data actually in the future. And I end now my section on telling you what segregation is and why we are interested in it with this plot here, which was done by Pavel Lejček. He's the Pope of segregation. And he has compared the DFT calculated segregation energies in red here with the experimental values, and you see strong discrepancies. And so this is still ongoing research to understand what plays a role when you compare this data to, so DFT to experiment. And in this case here, this is Auger electron spectroscopy data, so it's not APT, but a little bit different. So in general, we need more data, and for that purpose, we have thought about creating a repository for segregation data now, where we combine a lot of different sources, experimental sources coming from atom probe tomography or from high resolution TEM or also Auger electron spectroscopy into a database, which can then be compared to results from DFT or molecular dynamics, maybe if people are using interatomic potentials, and then maybe also one can try to use some machine learning algorithms on this data. In terms of the sources, I have to say that Auger electron spectroscopy nowadays is out of fashion, so almost no one does such investigations anymore. So this is all, but there is a lot in the literature about segregation. APT is now really in fashion and is used a lot, so that's why we are focusing on APT. High resolution TEM will be very interesting, but it's also very advanced in terms of the effort, and so only a few data points can be expected here. So we are mainly focusing on APT at the moment. And yeah, I would like to go with this database towards also fulfilling fair data principles and also enabling then, that one can publish data as we have already, and license data as we have already heard in previous talks, right? Okay, so I was talking to Claudia at a certain stage when she was in Leoben. She was presenting these FAIRmat activities when I realized that actually there is similarities to FAIRmat. And so actually we came together, right? And we discussed this, and Claudia, made me aware of what is going on in this project. And so we decided to, try to set up a NOMAD oasis for grain-boundary segregation data and combine different groups to contribute data so that we can actually have more to analyze in future. Yeah, so the goal for this repository is that we get more data, as I just said, that we have different experiments or different sources also, that we have a common tool set for grain boundary access evaluation, which I think is also important. So there may be different sources for data, but we should have a common tool set so it gets more reproducible. And then maybe also to use machine learning algorithms for getting out more data from these experimental data sets. I think we heard about user benefits before, so I think it's very important that user contributing to this repository should also have a benefit, because otherwise they will not contribute, right? So I think that a big plus would be that we would have a common tool set to offer on this oasis, so that people can look at their grain boundaries with the same tools. I think that is a big advantage, and maybe tools that they do not have, right? They can easily share data with others. I think that also is an advantage, and one can compare much better results and see the trends, and then also maybe see the database as a form to publish data in future. Okay, here is just regarding time here. Just an overview of the different sources of data. I already said we are focusing on APT now mostly. We have a lot of literature data on O'Shea, which I did not think to maybe include also in the oasis, but I've seen today that there is also literature data now. Maybe that's also interesting, or it could be something in future also to think about. Yeah, so here is what we are in the end, what we need that an experimental contributor gives us at the moment. So this is basically the APT experiment provides time of flight data in its very raw form, and this is typically processed, and then we have our position of the atoms and what type of atom it is. That is basically where we start acquiring the data, although it would be much more interesting to start here. So I'm not an expert in this whole thing, in this basically experiment. I think Markus sitting here really knows all the details. Yeah, at the moment we start here acquiring the data, and then we actually would like to know what has occurred to the sample actually before it was analyzed, and also what is then in the end what the one who contributes the data thinks what the excess is, right? And for that we need a tool that can actually allow the contributor to make this analysis. What is very important is the metadata. That actually is very important to us doing the simulations, because for us, just a tip with the chemistry is useless if we don't know how it has been produced and what is inside, right? Especially the heat treatment, how quickly they cool down, quenched after production, is very important. Otherwise, we don't know anything. We cannot use our models. And so this information is really, really important for us. And we still have to figure out how to really do this in the best way, that if somebody contributes, then provides all this information. I think it goes into defining the right schema files, but this is also where we then need to talk, right? Yeah, so this should all be present with the sample, otherwise it's almost useless for us, yeah. Okay, so I just want to say that there are, since we talked a year ago, some tools have emerged, or we became aware of tools, right? There is the one of Markus Küppach, of course, which is already on the oasis. Then there is also an earlier version, which is also on GitHub, which is doing what we want to do, or what the one who contributes the data should also be able to see. And I think also this is something which we are aware of, that it's also existing also in the group of Peter Felfer. There are being developments now ongoing for analyzing also grain boundary access. The thing is that these tools, they were not available when we started then. And also nowadays, I think none of these tools, but I may be wrong, is able to make it very easy to the one who uploads, that he uploads the data, visualizes its own tip, and then also makes an evaluation for the grain boundary access. And we are ready to switch, of course, also to these tools when this is possible. But for the moment now, I would just like that Alex presents what he has basically implemented on our oasis. So I hope Alex is there. I can see him. Yeah.
Can you hear me?
So basically, Alex did all this work and wrote a Python tool, a very simple one, that enables a contributor of data to upload his data and tell us what he thinks the grain boundary access is. And so, yeah, this is all work in progress. It's not finished, but it's already in a stage that you can get an idea of what it will look like. All right.
Okay. Hello, everyone. I will shortly demonstrate on our oasis how to use the tool that I've written. Okay. So I'm now, as I was saying before, on the oasis from Leoben, and when I then go to analyze to the remote tools hub, to the APM tools, I can launch it, which will launch this guacamole client with a Jupyter Lab inside. And I've prepared it here under the shared folder, the newest version of my tool, which is in a Jupyter. So it's a Jupyter notebook, very easy to use. Just just run it, and it looks something like this. So this is the graphical user interface. It is separated into 3 pages. You have a load page, a visualize page, and a calculate page. As Lorenz was saying before, I use the position file and the range files of the APT specimen. You have to here select it from the upload folder. You have to search for your ID, which I have prepared here, and just select those 2 files basically, and then load your tip. For some additional information, there's some text written on the load file, and at the start it will show you a low resolution image of the tip of the working, so like this, yeah. When I then go to, I can already turn it around and zoom in, but it's a little bit small. So if I go to visualize and, for example, plot it again, I already have a little bit of a bigger version of it. Here I can change the image size to make it smaller, depending on the resolution of my screen, what best works for me. I can select the amount of atoms which I want to show. For example, here on top of the screen, you can see I selected now 900 atoms, which is 1/5000 of all the atoms. And I can also choose the atom type that I want to show. In this tip, I know that carbon and boron is segregating under the grain boundary, so I select, for example, here boron, and I know there's only a few amounts of boron atoms, so I select the number very high so that it basically shows all the atoms, all the boron atoms, and then I can see here there's an accumulation of boron atoms. I can make it a little bit bigger, and I can also, for example, hide the axis, so if it's in the way, I can see that the grain boundary is along here. And what I can also do now is I can select along this grain boundary my region of interest, where I want to look at the concentration profile, which is in the form of a cylinder. And to align the cylinder with the grain boundary, I can basically select the grain boundary by setting some control points, which I do by just pressing Shift and left click, and then it selects some points on the screen, and the coordinates are marked here. You can see they are now set, and I can also print them out. So everybody knows what kind of control points I basically selected. And I can show then the fit plane as well. So it goes along my grain boundary now. It's a little bit to the side. And I can automatically set my cylinder along this fit plane. And I see that it's a little bit too much to the side, so I can select some more points, for example, on this edge. It should be more towards the middle now. I've had to adjust the cylinder again. It's now a little bit almost, but okay. Okay. Maybe I selected some extra points which are not needed. But yeah, if you have to do, want to get it like perfectly right, you have to like really specify what kind of control points you are looking at, and and where do you want to place the cylinder. If you're not very happy with how your cylinder is placed, you can still change the coordinates yourself, like make it a little bit higher up, and then basically check it again. So yeah, for example, And then I can basically already plot my concentration profile along the cylinder. And I see here there's a peak at some area, which is at the grain boundary. And then, like Lorenz said before, we are interested in the excess. And I can plot basically the total amount of atoms and can fit the excess by basically fitting 2 lines here by selecting 4 points, and very easily getting this the difference between this along this bulk region here and the grain boundary region. This difference is calculated then and is output as the interfacial excess here in atoms per nanometer squared. So this is then the thing that we want to compare in our work. So this already concludes what this tool can do. It's limited to this special use case, but it's very easy to visualize and to basically calculate the excess from a tip. Yeah. So thank you for your attention.
Thank you, Alex. So I will just finish. I think we're a little bit over time. Yeah. So this is what we have done so far. We're looking forward now to start this collaboration with our experimental groups, and also collaboration with Markus, who is really experienced in APT, and probably then in the future also use your capabilities also for automatic evaluation of the grain boundary and so forth. But yeah, I also end here. Thank you very much.